In this video, we're going to go over topic 8.2. And so we're going to be talking about thermal radiation and why greenhouse gases are impacting our environment. Okay, to do that, we're going to have to talk about conduction, convection, and thermal radiation. Okay, so under understandings, we have that we did touch on these briefly in topic 3 when we talked about thermal energy. We did touch on these. And then we're going to go into 3 aspects that I consider to be largely in the realm of astrophysics. Okay, the concept of blackbody radiation, however, applies here on Earth, and it describes how anything with a temperature radiates, basically radiates electromagnetic energy in the form of heat. Okay. And then we'll talk about 2 words that we don't see in general, albedo and emissivity, the solar constant, and basically the greenhouse effect and how that's impacting the energy balance in the Earth's surface atmosphere system. Okay. Under applications and skills, we have all this. Kind of some of the new things in here are the Stephon Boltzmann law and the Wien's displacement law. We did again touch on these very briefly in the thermal unit. But we're also going to be looking at primarily the Earth. Okay. Under formulas, we have quite a few formulas. One is the definition of albedo down on the bottom. The top one is the Stephon Boltzmann law that says power is equal to emissivity, the Boltzmann constant, area, and the 4th power of temperature. Okay, and so that one's interesting there. Okay. And then we'll be looking at Wien's law, which is basically the maximum wavelength, the peak wavelength for a given temperature. And then intensity is power divided by area. Okay, the guidance is shown here. We have 4 gases that we're going to be considering. CH4 is methane, H2O is obviously water, carbon dioxide is CO2, and N2O is nitrous oxide. Okay, and then we'll also be looking at some other things. Okay, so heat transfer. Okay, these are actually the same slides that from topic 3, but there are basically 3 different ways to transfer heat: conduction, convection, and radiation. Conduction requires direct contact between 2 objects. The one with more thermal energy, effectively more with more temperature, greater temperature, gives energy to the colder one. Okay, in convection, okay, this is going to happens in gases and liquids. It requires the bulk transfer of liquids or gases. But the one we're going to be mostly concerned with is radiation. Okay, and in this case, the energy is transferred via electromagnetic radiation, basically light photons. The light photons don't have to be visible light. Okay, we have the ability to have infrared, which is what we're most familiar with, but also into the ultraviolet and some of the other energy bands. Okay, I'm going to go very quickly through conduction. This is in the textbook, and it does say we don't need to know the formula, but it does require surface-to-surface contact, and energy goes from the hotter object to the colder object. Okay, so the rate of conduction is governed by this formula. Okay, Q over T is the rate of that energy is being transferred. K is basically thermal conductivity. A is the cross-sectional area, and the delta T on top divided by the distance of the contact zone. That's shown here in this picture. Okay, if you consider Q over T to be similar to current, remember charge over time. Okay, the hot versus cold is delta V. And Ka over D is the resistor formula, okay, rho A over L. This is almost identical to Ohm's law with the substitution of the resistivity formula. Okay, convection is the bulk movement, okay. We end up with convection currents based on the density of hotter or colder things, okay. And so warm air or warm liquid generally rises because it's less dense, and colder air comes back down. Okay, this happens not only in Earth's atmosphere, but it also occurs within the Earth, okay, which drives our plate tectonics. Okay, that moves us to the first thing that's kind of new in topic 8.2, and that's blackbody radiation. Okay, Wilhelm Wien actually got a Nobel Prize in physics for this in 1911, okay, and he basically said that everything Okay, everything with a temperature greater than absolute zero emits electromagnetic radiation or light. And since we have nothing at absolute zero, it's basically everything. Okay, and this blackbody radiation is summarized in the Stephon Boltzmann law, okay, where that E epsilon, okay, is the emissivity. When epsilon equals 1, the object is considered an ideal black body. Basically, it radiates perfectly. Okay, not everything radiates perfectly, but we're pretty much focusing on the black body ones, okay, when epsilon does equal 1. Okay. That sigma next to there, okay, is actually the Stephon Boltzmann constant. It has the value of 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the fourth. Okay, A is the surface area of the body. The surface area of a sphere is in the data booklet. It's 4 pi r squared. And T is the temperature of the body in Kelvin. Okay, and so it's kind of interesting to notice that like it's T to the fourth, and that's a big power. Okay, and so there's a lot of power that's being radiated. Okay, that's what we're doing here. Okay, how much power is being radiated by the body at a given temperature? Excuse me. Okay, so a black body. A black body is considered to be both a perfect radiator and a perfect absorber. Okay, at high temperatures, the light emitted is going to cover a wide portion of the electromagnetic spectrum. Okay, that's kind of represented in the graph down below. Okay, the longer wavelengths are to the right. Longer wavelengths are lower frequencies. Sorry. But they're all traveling at the speed of light, which is 3 times 10 to the 8th meters per second. So that 5,000 K curve, okay, that you see there, that's close to the temperature of the sun. And you can see that a large portion of the light is actually in the visible spectrum. Something that's colder at 3,000 degrees Kelvin, okay, doesn't have as much visible light, okay. So that's what happens at high temperatures. At low temperatures, the black body absorbs all electromagnetic radiation that falls on it. Okay, so temperature distribution. So Wien's displacement law basically says that the peak, so if I look at that curve, okay, it's not average or anything like that. It's not the mean, okay, but where I have the most intensity, okay, the most of the photons, well, not most, okay, the photons with the greatest number have a value of 2.9 times 10 to the minus 3 Kelvin meters over that temperature. Okay, so we have several different temperature curves here, 6, 5, 4, 3 thousand degrees Kelvin. Okay, again, our sun is between 5,000 and 6,000 degrees Kelvin, so most of the light from the sun is in the visible spectrum, at least visible to us, and there's probably a biological reason behind that. Okay, so not covered in this topic, but some people may be interested. This is how we can. This is a way we can categorize stars. Okay, because we can see what kind of light or where is the frequency most common coming from this star. So a blue star, okay, like Sirius, is considered a blue star. Our sun is considered a white star. Okay, it has a temperature somewhere between 5,000 and 6,000 degrees Kelvin. Okay, but the blue star has frequency in the higher range. That's why they look blue to us. Okay, and actually a lot of the energy there will be there will be quite a bit in the ultraviolet range as well. Red stars, okay, as suns cool down and they start burning helium instead of hydrogen, they turn into red stars. And so again, if you look at the peak light for the red star, that's pretty much in the red zone or into the infrared zone. Okay, so let's look at a worked example. Okay, by what factor does the power emitted by a body increase when the temperature is increased from 100 degrees Celsius to 200 degrees Celsius? Okay, well, we're looking at power, so we're going to be working with this formula. Okay, power is equal to epsilon sigma area T to the fourth. Since we're comparing it at 100 degrees Celsius to 200 degrees Celsius, area is going to be the same. Okay, emissivity is going to be the same, and sigma is going to be the same. So really, all I'm really comparing is P before, which is going to be T to the fourth, divided by P after, which is also T to the fourth. Okay, so before, this is going to be 100 degrees to the fourth, divided by 200 degrees to the fourth. And if you get 1/2 to the fourth, you're wrong. Okay, because this is in Celsius. Okay, this is in Celsius. This, however, is in Kelvin. So we need to make that conversion. Okay, the 100 is no good. Okay, it has to be 373 and 473 to the fourth. Okay, so again, remember, when do you need to convert from Celsius to Kelvin? Absolute temperatures, Kelvin. Delta temperatures, Celsius. Okay, so our star. Okay, stars and our sun are basically considered to be black bodies. They're perfect radiators of the energy. Okay, so the epsilon there would be 1. Based on the temperature and size of the sun, okay, the sun puts out about 3.9 times 10 to the 26 watts, or joules each second. Okay, most of that radiation goes out into space, but a little bit of it reaches Earth based on our cross-sectional area of the sphere at the Earth's orbital radius. Okay, so our orbital radius is about 1.5 times 10 to the 11th. It does vary based on the year and what time of the year. And based on the intensity formula, which is power divided by area, Earth, as we mentioned earlier, receives about 1,400 watts per square meter. And that's going to be what we call our solar constant S. Okay, because every second of every day, the Earth receives about 1,400 watts per square meter on the sun side. Okay, on the moon, on the dark side, we're getting nothing. Okay, so that introduces us to the word of albedo. Okay, albedo is the ratio of the scattered power to the incident power. How much energy do I radiate out? Okay, or do I not absorb versus incident power? Albedo can basically considered to be power reflectivity. Okay, an albedo of 1 is like a perfect mirror. It basically reflects all the power. An albedo of 0 is basically perfect absorber. It absorbs all of the power. So for instance, snow has a very high albedo of 0.85, whereas charcoal has a low albedo of almost 0, not quite 0.04. Earth, however, has an average of about 0.3. Now this 0.3 varies by a whole bunch of factors like location, weather, season, all sorts of things. Okay, but if we want to average it over the whole Earth, we call it about 0.3. Okay, so solar intensity. If Earth's average albedo is 0.3, that means 30% of the sun's energy is reflected. Okay, and 70% of the sun's energy is absorbed. The average during the day is going to be half the maximum because the angle that the sun hits us makes a difference. Okay, that averages out, again, because of square roots and things like that, to about half. Okay, and again, multiplying by another half because half the time we're in daylight, half the time we're in night. Okay, the average daily power that hits, average power turns out to be about 245 watts per square meter. Okay, if I averaged over the full 24 hours. Okay, not just during daylight hours. Okay, if you remember, we had a maximum of 1,000 watts per square meter on our previous slide. Okay, that 1,000 was a maximum, remember. This is more of an average. Okay, so the energy balance. The Earth generally maintains a constant temperature. Ignoring, over the long term, it may go up, it may go down. Lately, it's been going up. Okay, but for, in general, it maintains a constant temperature. That means, okay, that the incoming energy must pretty much equal the outgoing energy. And if I do kind of a simple diagram, it's not exactly a Sankey diagram, But here I have the incoming intensity I. 30% or so is reflected, 70% is absorbed. That Earth, however, also radiates, okay? It's got a temperature, it's an object, so it radiates that energy back out at our temperature, okay? And so that energy must balance out our incoming intensity, okay? Otherwise, our temperature starts to increase, okay? And so here's an example that we can work, okay? This one I'm not going to do, it's in the textbook, okay? But it assumes that the Earth has a fixed temperature and that it radiates as a black body, okay? And when I go through this, okay, Earth's constant temperature actually turns out to be, I believe it was minus 17 degrees Celsius. Let me just look that one up so I give you the right number. Yeah, the temperature current turns out that Earth should be maintaining a constant temperature of about minus 17. But that number is going to be off, okay? Obviously, where Earth's average temperature is not minus 17. It's actually above zero at this point, about 288, I think it was, okay? But that's because this is a simple model. It assumes that all the radiated energy from the Earth, okay, that up arrow, basically makes it back into space. And in actuality, it doesn't. And that's because of the greenhouse effect, okay? Our average temperature right now is averaging about 15 degrees Celsius, okay, which puts our radiated energy in the infrared range, okay? And the way greenhouse gases work is they absorb that temperature, okay? They absorb light at that wavelength, okay, in the infrared range, okay? And when they absorb it for a short amount of time, and then they re-emit that energy. But they re-emit it in all directions. Half of those directions pretty much back into space, half of those directions back to Earth, okay? And the more greenhouse gases I have, the more of that radiated energy is absorbed and reflected back to the Earth. Now, some balance is good because I don't really want an average Earth temperature of minus 17. Okay, during our ice ages, okay, that may have been the case. Okay, for whatever reason, the greenhouse gases during those periods dropped significantly and we radiated the energy into space. Okay, and it required, again, a significant output of greenhouse gases, largely because of volcanic activity, to put us back in the range where we can more or less enjoy the temperature. Okay, so greenhouse gases. There's basically going to be about 4 greenhouse gases that we need to worry about. Okay, water vapor, carbon dioxide, methane, which is CH4, and nitrous oxide, which is N2O. Okay, now all of these things are naturally occurring. Okay, carbon dioxide is probably the one that pushed us out of the ice age into regular, into our current warming period. Okay, and that's also the one that's driving our greenhouse gases to a large extent. Okay, methane is another big one though. Okay, so during the ice age, okay, all of these gases were probably relatively low. Okay, but whether it was a meteor impact in the oceans, which put a lot of water vapor in our atmosphere, or volcanic eruptions that put a lot of carbon dioxide, something moved us out of the ice age into this our current warming period. And then human activity is also pumping a lot of carbon dioxide into the air. Okay, and so how do those greenhouse gases actually absorb energy? Okay, it turns out that the electrons in the molecules, okay, whether it's a carbon dioxide molecule or water vapor or methane, okay, the electrons in the molecule occupy specific orbitals. We'll talk about this when we get into the quantum physics and the atomic physics. Okay, but they occupy orbitals and they can absorb energy. When they absorb energy, they move up to a higher orbital level. Okay, they can actually absorb enough energy to free themselves from the atom, but for the most part, they just they absorb some energy, they move up to a higher level. Okay, and then when they come back down to that lower level, okay, which is where they want to be because it's a lower energy state, it's more stable, they emit that same energy back as a photon. But there's no specific direction that that energy is released, okay? It's pretty much purely random in all 360 by 360 sphere degrees, okay? And so sometimes that energy will head back out to space, as it should, and sometimes that energy will be redirected back to the Earth. Okay, thank you.